To carry out the formal Bohr Sommerfeld analysis, you will recall, because now we're in a 1D system, it's a new type of system, we have to go back to the original basic definition. The original definition was that we had an integral over a complete cycle, that's why I drew it as a closed loop integral, of the momentum times the displacement, and that always must equal some integer n times Planck's constant, where n varies. This quantum number has values 1, 2, etc. And now, because I'm in one dimension, one thing that I can do is to simply write this as p times dx. Because in one dimension, the distance, of course, plays the role of x. So this is the integral that we have to carry out. And if we're going to carry out such an integral, clearly I want to understand how the momentum depends upon the position. So let me draw a plot for that. So that will be my momentum axis, p. This will be my position axis, x. And if we want to sketch out how this momentum depends on position through a full cycle, we may as well begin, say, at the maximum displacement, at x max. So there's going to be a certain maximum displacement, x max. And just like with the hydrogen atom, ultimately we want to solve for everything in terms of the energy so that we can generate an equation which can be solved to give us the energy in terms of the quantum number n. So let's solve for this maximum position in terms of the total energy of the oscillator. Now the Hamiltonian is numerically equal to the energy of the oscillator. And at the maximum position, of course, that's where the velocity instantly is 0, so there's no momentum, and so 1/2 kx squared equals that energy. I can solve for x. That would be 2e over k square root. So that will be the square root of 2e over k. Now, we know next what happens to our particle. If it's sitting at this maximum position, initially it doesn't have any velocity, but the spring then begins to pull it inward, and it begins to pick up some negative velocity and negative momentum. Initially, the position doesn't change much because instantaneously the velocity was 0, so position initially doesn't change much, but the momentum starts to decrease, like so. And then as time goes on, I continue moving along some kind of curve until I cross x equals 0. At that point, the spring is no longer pulling me to the right. The spring is now compressed. It's trying to slow down the particle, so the momentum will hit a maximum value just at x equals 0. The particle has that momentum. It then continues along, slowing down. So as it begins to slow down, the momentum is less negative, and it will do that until it reaches a minimum position, which is this location here. Now that minimum location, of course, has the same amplitude, but it's on the opposite side of the equilibrium point, so there's an x min here that is just minus the square root of 2e over k. And I noticed here I neglected to think through what the minimum momentum would be. So that's a negative value. And the value of the momentum at that position where x equals 0, when I insert x equals 0, I now solve this equation for the momentum. I multiply by twice the mass and take the square root. So that's minus square root of 2me. And then the particle has kind of been tracing a curve like this. Once I hit the minimum point, the compressed spring then begins to push the particle forward. So I'm going to then move up into positive values of momentum. And as you can see, I'm tracing out a very beautiful curve. It will look symmetric, something like this. The maximum momentum will be plus square root of 2me by the same type of arguments. Now, this curve that we've traced out, two things to say about this diagram. The first, when you trace out how a particle is behaving on a graph like this in terms of momentum and position, this kind of diagram is called a phase space diagram. And the second thing I would like to notice is that the particular figure that the harmonic oscillator traces out obeys, of course, this equation, and this is exactly the equation for an ellipse. It looks very much like the equation for a circle, x squared plus y squared, but there are different constants multiplying x and y, and so different axes are stretched out to different amounts, and that's why this is actually an ellipse. And it's very useful for us to know that this is an ellipse because if we think about the phase space diagram we've just traced out, the integral of p dx, well, integral of p dx, that should be the area under this curve when I'm going in the forward direction. And when I go in the negative direction, you'll notice both p and dx are negative, right? So I also trace out an area, and now it's a positive area once again because p and dx would both be negative. So in the negative excursion of this, I'm tracing out the bottom area of this. And in the positive excursion along the upper half, that's just an integral again. So that's just giving me this positive area. This integral just gives me the area of the ellipse. So what I have then is n times h equals the area of my ellipse. And you may recall the formula for area of an ellipse. It's very much like a circle. A circle is pi r squared, but here we kind of have two different radii. Those radii, quote unquote, are actually called the semi-major and minor axis. So it's pi times the semi-axes, pi times a times b is the standard formula. So that's pi. This axis is square root of 2e over k. And then the other axis would be this axis, whose size is square root of 2me. And now we just have some algebra to do. One thing I'll notice is that 2e appears in both square roots, so that comes out as just 2e. So I have a nice factor, 2 pi e. Oh, I like that, because whenever I have a 2 pi, I feel good, but especially good because I can bring it to the other side of the equation and make my h into an h bar. So I'm happy about that, but let's finish our algebra. So we took care of the 2e factors in both, but we still had a square root of m on top and a square root of k on the bottom, so it's square root of m over k. And finally, we can solve this equation for our energy levels E in terms of n. And when we do that, we divide both sides by 2 pi. So I'll have n times h over 2 pi, which is h bar. And just to remind you, this came from h divided by 2 pi. And then to really solve for E, I need to put this on the other side of the equation where it flips over and becomes square root, oh, very nice, k over m. And that is very familiar because that is just the natural frequency, the natural angular frequency for my oscillator. So n times h bar times omega naught, the natural frequency, that is my formula then for the harmonic oscillator. Now, look at this. This is really cool because this is just h bar omega times an integer. So that means at every integer multiple of h bar omega, I get an energy level. This would be n equals 1, n equals 2, n equals 3, and they all have the same constant spacing between them. The spacing is h bar times omega naught. So our intuition that we should have perfectly constant spacing has been perfectly borne out here. So our key observations in this one are first that delta E in this case is a constant. That's very exciting. That's what the correspondence principle told us we should expect. So we had anticipated that. The second thing is, well, we can now check, does this change in energy equal Planck's constant times the classical frequency? That's a question mark, right? Because this is the this would then tell us that the frequency of radiation coming out actually matches the classical frequency of the oscillator. Now, we had worked out the classical frequency of the oscillator. Previously, it was 1 over 2 pi times let's see, where did we have that guy here? It was 1 over 2 pi times the angular frequency. We had it written as 1 over 2 pi times the square root of k over m, right? But h over 2 pi is just my h bar, and square root of k over m is my h bar omega naught. And so indeed, we also get complete correspondence. The radiation that would come out of this thing comes out at exactly the correct frequency. There's one final observation we need to make, however. So all of this is super exciting. But there's one thing, which is that the true answer isn't exactly what we got here. The true answer is, and you can get this from experiments if you want, that En is equal to not n, but n plus a half h bar omega, where in this case n can start at 0 and then be 1, 2, etc. So really, instead of getting the positive integers 1, 2, 3 times h bar omega, I get like the halvesies, right? It starts at 1/2 and then 1.5 and 2.5. So it's 1/2, 3 halves, 5 halves. Not quite what we had predicted. And that's important because it's very important for you to understand that the Bohr Sommerfeld quantization is not exact. You might get that impression because it actually did turn out to be exact for the for the hydrogen atom. But here, and what was beautiful about that, by the way, was there was no order of magnitude estimates and fudging factors of 2. It gave us a clear, crisp prediction. And it also gives us a clear, crisp prediction for the harmonic oscillator. It just happens to be off just a little bit. It does very well on the spacings, but there's this like slight shift by 1/2. And that is an indicator, I think, that the de Broglie hypothesis has all of the correct physics in it, right? But that we just haven't built up a sufficiently accurate and formally thought through theory. But now that we really see the successes of the de Broglie hypothesis, this slight discrepancy is a clear indicator that we need some deeper theory. And that's where we will be going next.